Welcome back to Predictive Analytics Regression and Classification lecture series. And today we are going to start lecture 5, part A. In this lecture, we are going to discuss the how to check model assumptions. So as usual, we start with the model like y equal to x beta plus epsilon linear model or linear regression model with epsilon follow normal 0 sigma square in. So I'm writing it as a matrix notation, and remember that y is n cross 1 vector, response vector, x is n cross p matrix known as design matrix. Typically it will be containing the covariates, predictors, or sometimes it called features. So this n cross p, beta is the regression coefficient or weight matrix, typically called regression coefficient, and epsilon is the n cross 1 residual vector. Okay, a vector of size n of residual, or the part of the model which you cannot explain. The model has 4 assumptions. One is the linearity. That means data is in a linear hyperplane. So you can think of that model is actually some functional form of x plus epsilon. Now this function could be any function, but when you are saying that y is equal to x beta plus epsilon, then you are having a particular form of model, and that is called linear models, and that's the major assumption. And how do you check whether the linearity that you assuming in the hyperplane, the linear hyperplane that you are assuming for this data, is it a right assumption? Second assumption is independence. And when you assume independence, that means basically ith observation, the residuals of the ith observations and residual of the jth observation, their covariance is 0, or they don't have any correlation. That means they will not have any correlation. They are independent. That is conditionally they may be dependent, but the residuals will be independent. Third assumptions is known as homoscedasticity. That means all residual have same variance. All residuals have the same variance. Okay, for all I 1 to n. And then the fourth assumption is Gaussian distribution, that this epsilon follow normal 0 sigma square. See, this Gaussianity is the one of the major fundamental assumption that we are making. So the first we will discuss how to check the linearity or data, that is data is in hyperplane. So how to check the linearity? So it's difficult, particularly in maybe if you have only two variables, say y and x, then you can simply draw the plots and you can check whether they are in a linear or not linear. But if you have multiple independent variables, like you have data with y x1, x2, xp, many variables, and that means your data is in a p plus 1 dimensional geometry. then it is very difficult whether the data is, the model is in really a linear hyperplane or not. Now, what can you do? One visualization technique is you plot the fitted values versus the residual values. So you plot the y, you first fit the model beta naught beta 1 x1 plus dot 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 beta 2 x beta p xp. You fit this model plus epsilon, and the fitted model you calculate the y hat and the epsilon hat, and then you plot these two. Plot epsilon hat on the x-axis and y hat on the y-axis. And once you, if you do not have any pattern, then you can say that it is actually probably a good that linearity assumption is probably a valid assumptions. Okay, so what we have done, that first we fit the model using lm function, remember, and then we are calling it, okay, give me the summary of the fit. And then what we are doing from the fit, we are taking the fitted values, and from the summary we are taking the residual values. Okay, and then we are saying that plot these two. These are the graphical features, bunch of graphical features we have given: y labels, x labels, the limit of the y-axis, and all these things. And we draw a AB line at the horizontal line, and we have also asked to draw a grid, and we plot some of the things. Okay, now when we run this piece of R code, if we run this piece of R code, what we find is this. On the x-axis we plot the fitted values, the y hats. On the y-axis we fit the residuals, the error, and we can more or less say that there is no major correlation or major pattern that we see in this fit. And we also calculated the correlation between the residual and y hat, and we found that they are almost zero. I mean, it's all practical purpose, that it's saying basically after decimal you put 17 zeros and then 6 4 5 5 8 1 7. So all practical purpose, if you round it even up to 8 decimal places, it's zero. So we can't find any correlation between the residuals and y hat. So, and also visually we see that there is no major pattern between the two. Okay, next we will check the second assumption, test for randomness to check independence. So what is our null hypothesis? What we will do here, after fitting the model, we have these errors, right? We have these errors, E1 hat, E2 hat, En hat. So this is after fitting the model, we have y hat, which is x beta hat, and then we also have the y's. So we can compute the E hat from y minus y hat. Okay, now E hat is basically our E1 hat, E2 hat, dot dot dot, En hat. Now question is this number, are these numbers, is this vector, or the numbers of this vector are random numbers or not random numbers? That is the question that we are going to ask. So the null hypothesis, we are saying that yes, these are indeed random numbers, and alternative hypothesis, these are not random numbers. So there are three popular tests are there. One is Bartle's rank test, 1984. Bartle's, also known as Bartle's ratio test. Second is Mann-Kendall rank test for randomness. And the third is Wald-Wolf-Ruiz rank test for randomness. So in which Bartle's rank ratio test is comparatively a newer test with a better statistical power. So from the R package, we have in the R package we have called the rank test package, to which implement the several non-parametric randomness test for of hypothesis. Okay, so we have done here the Bartle's rank test because it is a new test comparative the more popular ones, and we know that statistical power for Bartle's rank test is better than the others. So we call the library rank tests, and in that rank test there is a function called Bartles.rank.test, and you just supply the residual values from the fit. So if you basically, I'm saying we have done this fitted model, from that you extract the residuals. That is what this dollar sign is, basically extract the residuals as a vector and supply this as a vector in the Bartle's rank test. Then it will run the test. The statistics is negative 0.9857, sample size is 32, and the p-value is 0.3243. In this test, alternate hypothesis is non-randomness. So the null hypothesis is randomness and alternate hypothesis is non-randomness, and p-value is since quite large, so we fail to reject the null hypothesis. So we stick to, in this particular test, we stick with the null hypothesis that these residuals are random indeed. Next, we will move on to the discussion for homoscedasticity versus heteroscedasticity. So when the variance for all residuals are equal, we call that homoscedasticity. So this is what we are talking about. So homoscedasticity is variance for all the residuals are sigma square. This is same for every residuals, and this assumption is typically called homoscedasticity. Now, when the variance of residuals are different for at least one case, we can call this as a heteroscedasticity, and the alternative is called variance of epsilon I is not equal to sigma square, at least for at least one I. Okay, so this is my alternative hypothesis. So equal variance across, so null hypothesis is talking about equal variance across the population is called homoscedasticity or homogeneity of variances. Homogeneity of variances. If the equal variance does not hold, then it is known as heteroscedasticity or simply heterogeneity. If somebody says that there is a heterogeneity in the data, basically that means they are saying that the variances of residuals are not same. So question is, how can we check homoscedasticity? There are quite a few many actually tests are available. One very popular test is Bruch-Pagan test, then Bartle's tests, Box's M test for homoscedasticity in multivariate data is also available. Okay, so these are multiple tests are available. Now, first we will discuss What is Bruce-Pagan test? So consider a general form of variance, okay, and variance of yi is essentially expectation of ei square, because you can effectively say expectation of ei is 0. Particularly if you are using OLS method, then you can show that E bar, the sample mean, will be very close to approximately equal to 0. You can pretty much show that. Now, what here we are thinking is to show this E square, expected value of residual square, is some function of z1, z2, zq, where what are the z's? z1, z2, z3, these could be the same or different from x1, x2, xp, or some functional form of x1, x2, xp, but some predictors. Okay, now if all the gamma 2, gamma 3, gamma q, all these guys are 0, if all of them are 0, then what happens? Then I am saying basically expected value of ei square is equal to g of gamma 1, a constant, right? Some sigma square. Okay, but if at least one of gamma is non-zero, then it is not same. So this is the test that we are going to do, that gamma 2, gamma 3, gamma q are all 0 and at least one gamma I is not 0. The dependent variable ei square are unobservable, remember that, but substitute with the least square estimate ei hat square. So this is unobservable. Okay, this is unobservable. So what we do, we, instead of directly working with the ei square, we work with the ei hat. Okay, so that is what we do. Now, what turns out that the R square that there is a chi-square statistics that n times R square, it follow chi-square distribution with q minus 1 degrees of freedom, and in the LM test package in R, it contains a function called BP test, stands for Bruce-Pagan test. In Python, in stat models module, if you have to call from the stats model, you have to call the stats, and then from diagnostics, you have to call this head stands for heterogeneity, Bruce-Pagan. So test for heterogeneity using Bruce-Pagan. So in Python also the Bruce-Pagan test do available. So either you can use Python, or you can use R. Either way you can run the Bruce-Pagan test. It should give you the same thing. Now when we run the Bruce-Pagan test using LM test in the R, if the heteroscedasticity is present, to check that, so all we have done, it's a 2-line code, is basically call the library LM test and run the BP test, and then in that you just pass the fit, and that will give you the Bruce-Pagan test, and that is P. And what we found, that the P value is 2138, 0.2138, which is large enough, and hence we failed to reject the null hypothesis. So since we failed to reject the null hypothesis, so we can safely say that at least for this test, this model, the Bruce-Pagan test is failed to reject the homoscedasticity. Hence, assumption of homoscedasticity is reasonable for this particular data set or this particular model. Finally, we will check the fourth assumption called check normality for QQ plot. Now QQ plot is very popular. All you have to do that calculate the quantiles, theoretical quantiles of normal distribution, and you calculate the sample quantiles from the data, plot them, and if they are indeed coming from the same distribution, then they should be on the same line. So that's what you do. So, and in this case visually looks like they are on the same line, however on the tail side these points are looks like going far away from the line. So looks like normality could be a questionable thing. So let's try to check if how the residuals, histogram of the residuals looks like. Now what we are seeing, since we have only 32 observations, it looks like that that it is little bit maybe off from the normality, but it's a bit difficult to say. So what we can we do a test or hypothesis to check the normality? So that to check the normality with statistical test, the most popular one perhaps the Kolmogorov-Smirnov test, what basically assumes that the residual follow normal 0 sigma square versus residual does not follow normal 0 sigma square. So the Kolmogorov-Smirnov test statistics is essentially square root of n, and this would be E, and Fn E minus phi sigma E, and you subtract that, take the absolute value and supremum of that, and that will give you the Kolmogorov-Smirnov test statistics. And if it there will be a K alpha level critical point, and if the Kn is greater than K alpha, you reject the null hypothesis. So that is the way we do Kolmogorov-Smirnov test at an alpha level percent. So in R you have ks.test, from the stats package, and just run the Kolmogorov-Smirnov test. And in Python from SciPy you just call the stats module, and from there you just have the ks test to run the Kolmogorov-Smirnov test. So in both R and Python you have all these. And so other than Kolmogorov-Smirnov test, there is also Anderson-Darling test, Shapiro-Wilk test. There are also other tests are available. So I did run the Kolmogorov-Smirnov test for residuals, and that is basically case.test. I just subtracted the residuals and then give that p norm. Basically I'm asking Kolmogorov-Smirnov test to run it against the normality, and exact one sample Kolmogorov-Smirnov test was run, and what we found that p value is 0.006698. This is quite small a number, so we have to reject the null hypothesis. That is residuals are not normal. Residuals are not Gaussian distribution, not Gaussian. So this is a and you often find that I have often find in my career that many times residuals actually does not follow Gaussian. So for example, financial data, it rarely follow. I have seen in financial data rarely follow Gaussian distribution. So it is a very strong assumption in regular classical regression methods that residuals follow a Gaussian distribution. Now there is an alternative method, alternative test appears, that's called Shapiro-Wilk test. When we run the Shapiro-Wilk test, we found that p-value is 0.1217. So that means Shapiro-Wilk test fail to reject null hypothesis. Okay, null hypothesis. So that is that means it's saying that you can probably assume that they are normal. It is Shapiro-Wilk test is bit conservative in that sense in terms of rejecting null. So there is a doubt. Definitely Anderson-Darling test also, we have done Anderson-Darling test also. In NOT test library you have AD.test, which is stands for Anderson-Darling test for normality, and here also p-value is 0.1489, quite conservative, so it fails to reject the null. So in this case also that it says that residuals are probably following normal distribution. We don't have enough evidence to reject the null hypothesis. Now, what happened if any one of the model assumption is not true? If any one of the model assumptions is not true, then you should not use that model any further. In fact, my recommendation is you should consider using more advanced model or the model which stands with its own assumptions. And if we, in this particular case that I showed as an example, we see that though linearity makes sense, like probably is okay, assumption of linearity is okay, though we found homoscedasticity is okay, randomness is okay, but assumption of Gaussianness or Gaussianity could be in question. Out of 3 tests, 2 tests failed to reject, but 1 test did reject. In this case, I would say that if you want to be conservative, it is better you should consider a slightly alternate method, maybe a bootstrap statistics method or a Bayesian statistics method to overcome this issue. In later some of the lectures, I will talk about how to do bootstrap statistics with linear regression or Bayesian statistics with linear regression. A next big question, what happened if all 3 assumptions of the model are good? So I'll say that's a great news. In fact, I would say congratulations that you have overcome one hurdle. Now your duty is to go and check how good your prediction accuracy is. You can fit a model, and you found that okay, all model assumptions are correct, but you found that your predictive accuracy only 15%. Are you going to use that model? No, probably not. That's not a good idea to use that model any further. Okay, because yes, you have fitted a model with all assumptions correctly, passed through the test of test of hypothesis. Model assumptions are correct, but if the predictive accuracy is completely, through the floor, if the model predictive accuracy is very bad, then obviously that model has no predictive accuracy, and it defeats the entire purpose of developing a predictive model. So our goal is to develop a predictive model which will stand with its model assumptions from the data, as well as it will have a very high good predictive accuracy. So with that, I will stop here and we will move to the next part. And in the next part, we will compare the performance of 2 models. So we'll discuss how we can compare the performance of 2 models and different choices of model selection criteria.